Good morning, everyone. Thanks for joining this call. So today I'll be presenting on hardware for machine learning, as most of you know. And I did this project last year, as Ricardo mentioned, when I was a work-ready graduate program. And most of the work I did was, I'll better switch on my video, I guess. Yep. So most of the work I did was mostly literature survey, trying to summarize papers and trying to come up with the new ideas of how to do this. But for this presentation, I mean, the topic is a bit vague because this is a very big field. So before starting with the presentation, I'll just explain more of what we're going to talk about today. So when we say about hardware for machine learning, the first thing that comes to mind is usually, these big computers, supercomputers, GPU clusters, servers, or these big GPUs like the one which we have in CeADAR. So what we do is we train our models on these, and these are big, power-hungry, but very fast computers. But this is not what we're going to talk about in this talk. Instead, what we're going to focus on is small-scale platform for executing machine learning. These include, small devices like this robot out here. This is an NVIDIA robot. NVIDIA has its own platform for designing robots, and or something like OpenCV. OpenCV recently announced this AI kit, which has a few cameras in it, and you can see the scale of these. These are small devices. You might have heard of the word TinyML. So that's what we are going to discuss today. TinyML is about running machine learning algorithms on very small devices. The major difference between these devices and your big GPUs or servers is that these have very stringent memory and power requirements. So memory might be a few megabytes or even a few kilobytes in some cases, or a couple of gigabytes, not more than that. And power, these are like very small 2 or 3 watt systems, unlike your GPUs, which go quite up in this domain. Also, we're going to talk about software libraries like TensorFlow Lite. You might have heard of this. These are for running TensorFlow models, deep learning models on microcontrollers, which are small. So before we go into techniques of how you can run these big models on the small devices, I'll just show you the machine learning pipeline, because this will help you understand what all things can be changed to make these big models run on these small devices. So starting from here, what we have is a biological neuron. Neuron has dendrites, and it has a cell body, and then it has this big axon, and then it gives the output to other neurons from here. So what computer scientists have done, they have modeled this biological neuron into the simple mathematical model, which has weights. So these x1, x2, and x3 are inputs. These are multiplied by weights in this neuron, and then you have an activation function, which is basically your axon in the biological domain. So your output is a sum of these inputs multiplied by weights, and then an activation function acts on it. So this is the basic model of a neuron, which I think almost every deep learning network follows. Now, what you do is you pick up these neurons and arrange them into various configurations. One of these configurations is here. This is a simple feed-forward network. What you have done is you have put various of these neurons in layers. So one layer has multiple neurons, and you can have multiple layers in a network. These networks themselves can be biologically inspired too. For instance, convolutional networks, which many of you must have heard of, are very popular. They are actually inspired from your visual cortex in the brain. The cells in the visual cortex are structured in a similar way the neurons in your convolutional neural networks are structured. So once you have this network, what you do, you get your data and you train the model. These days, unsupervised machine learning is also getting popular, so you can train your model without data also in some sense, or without annotations, but more or less data is needed almost all the times. You train your model with the data, and then after training, you pack your model into an intermediate representation. And after that, you move that intermediate representation to a hardware system like this. This is Google's tensor processing unit, has a GPU and a big fan to keep it cool. Can you guys hear me?
Yep.
Yeah.
I can hear you.
Yeah, I guess there was some disturbance there. So this is an oversimplified version of the pipeline we have. Now what we're going to do is we're going to pick up portions of these pipelines and see how can they act and this in this hardware for machine learning domain. I mean, how can these various parts of these pipelines can be tuned. So let's begin with the hardware first. Let's see what we can do at this end of the pipeline to make our lives better. But what is the problem? Let's take an example of AlexNet. AlexNet is a popular network. It has 61 million weights and 724 million MAC operations to process one image. So if you input an image, it's going to have 24 million of these MAC processes. What are MAC processes? It's multiply and accumulate. So when we multiply the weights by the inputs and we add them, this is called one MAC operation or a multiply and accumulate operation. So if you look at this diagram here, in the hardware, what happens? There's an arithmetic logic unit in yours, almost in all your processors. It does all the mathematical operations you need. This is where your MAC operation is executed. What it does, it reads your filter, your weights of the neural networks from the memory. It reads inputs from the memory and it sums them. It accumulates the partial sum inside, and after summing the whole thing, it updates the memory with that sum. So this is what a whole MAC operation looks like. But the problem here is memory and energy. So these ALUs, these processing units within your processors are very small and have very few, very small memories. So for instance, you can think of your cache memory, which is like a few kilobytes or a few megabytes in size. But when you go to your RAM or ROM, those are like tens of hundreds or 1,000 gigabytes too. But the problem here is, so if is when you read weights from these memory, it takes power to get those weights, it takes energy. And if you consider the memory inside the LU, and let's take that as a reference. So let's say 1 unit of energy is required to get one of these numbers from the memory on the LU itself. So what you will see as you go higher up this hierarchy of memories, so there's a global buffer, or if you go to your RAM, you'll see when you go to your RAM, the energy consumption becomes 200 times. It takes 200 times more energy to get one weight from RAM than to get it from your local memory. So this is a major problem, apart from the size of these 61 million weights. And not just that, various researchers suggest that in neural networks, most of the energy is actually consumed in fetching the weights from the memory rather than doing the computation itself. So the computation, that's the multiplication of these numbers, actually takes less energy than getting those numbers from the memory. And this is the main problem that we have to address in the hardware when we want to make big machine learning models run on these end devices, which on low power. So let's look at what things can we do to our existing hardware, like a GPU or CPU. So your typical GPU or CPU is structured like this. You have a memory hierarchy, you have a cache memory, you have a RAM, you have ROM, and then you have registered files, and you have a control bus. So what this control does, it asks ALUs, your computing units, your main computing units, to read the memory and then perform calculations. And after reading from the memory, send whatever you have calculated back to the memory. This is how the most existing GPUs or CPUs are structured. Very high level overview. So when you talk about neural networks, I just showed you about these MAC operations. MAC operations, usually in hardware, they are converted to matrix multiplications. What is done that they take the filter layer and they multiply it with the inputs, and these are all matrices and they output a matrix. Same for like if there are multi-layered inputs, they do the same. They convert them into matrices and filter cells into matrices, and then you multiply these matrices and give the outputs. Now, what we have done here is we have in fact simplified this problem a bit. What we need to do to speed up neural networks or have them consume less energy on a traditional GPU or CPU is just optimize these matrix multiplications. And there are many ways to do so. One of the ways is here, cast data across memory hierarchies more efficiently. For example, suppose we know that we need to use the filters again and again. For that, what we can do is that we can, instead of keeping the filters here, we can keep them in the ALU memory, and that way you don't have to access those filters again and again. This is one example of casting the data efficiently. There are many more examples of this, but I won't go deep into that. The second thing is supporting multi-threading. So you know parallel processing and multi-threading. Can you do computation in such a way which are easily parallelizable? So you can do that also to the existing hardware. And the third thing, which I think most of you might not be familiar about, is like you can transform these computations. Instead of multiplying these matrices, what you can do instead, you can transform these matrices so that these operation becomes very easy. One of the examples is fast Fourier transform. So the convolution of two functions, if you take a fast Fourier transform of these, is actually the fast Fourier transforms of individual functions multiplied with each other. So what this means that instead of doing the whole convolution operation, what you can just do is you can individually get the Fourier transforms of both these matrices and just do a simple multiplication instead of convolution to make these things simple. So these are the kind of things that you can do on existing hardware. In the hardware terminology, this is called kernel. Your matrices are called kernels. So you will generally find this keyword accelerate kernel computation on CPU and GPU platforms. So if you want to look for more resources, you can go and use this keyword. But the two key examples are this Intel Math kernel library, which has code which you can use so that your deep learning neural networks or matrices are better casted onto your hardware. And many existing libraries, I think most of you might be familiar with NumPy or SciPy, use this internally to speed up their computations on Intel processors. Another very popular library is NVIDIA CUDNN, CUDA-DNN. NVIDIA GPUs, as we know, are very popular. So this is also very popularly used, this library. I was using PyTorch, and many of the PyTorch directives internally match onto this library. And that's why most of these libraries are very GPU oriented, and it's very easy to run them on GPU because internally they use NVIDIA's kernel library to speed up computations. So this was about existing hardware, but what kind of new hardware can we make so that this deep learning on the edge is more efficient? I must say, in some way. You cannot put a big GPU on a drone, let's say, or on an IoT devices sometimes. So you need even smaller hardwares than these. So in that direction, there's something called deep learning accelerators, which I use. What are these deep learning accelerators? These are specialized hardware which can speed up your execution of deep neural networks on this edge hardware. Most of these do not support training of the models. That means you still have to train your models on GPUs or CPUs. But what you can do is you can do inference on them. That means you train your model on your GPU, but after that you transfer the model to this, and then you can run inference on your device. A very good example of this is Movidius Neural Compute SIC. This is a USB kind of stick. Actually, I have it with me here, but yeah, you can see it in the picture. It's a USB stick that can plug into your device, and then you can run deep learning networks on it. So inside this USB stick is a myriad chip. This myriad chip is like a VPU, they call it. It's a vision processing unit, which is just a way to accelerate deep learning models, especially visual-oriented deep learning models. An example where this Myriad X chip is used is DJI drones. So this drone is a perfect example of kind of limitations these systems face. So, you know, drone batteries are small, and the rotors also consume a lot of power. So you need your deep learning model to consume very less power, and also you need it very fast because these drones are pretty fast and you need high throughput from these models. So you need both speed and low power for your deep learning networks to run on these kind of devices. Also, Movidius is a special company. It's an Irish company. The founder is an Irish, did his PhD from Ireland, and made this company, Movidius, made this chip, which was later acquired by Intel, and now this is their flagship product in deep learning accelerators. But so let's dig deeper into these accelerators and see what is the main difference between these accelerators and GPUs. So I showed you this typical structure of a CPU or a GPU before. Your ALU is structured and how they read from memory hierarchy, and there is a control. These accelerators are structured a bit differently as shown here on the right. The ALUs are interconnected. That means they can share memory within themselves also, and the controls are within each ALUs. And these ALUs also have more memory than your traditional CPU or GPUs have. And then the memory hierarchy is still the same. But what this kind of net kind of structure does, when you cast those computations onto this structure, it can become more optimized because they can share weights with each other and the memory is also high. One of the examples which can be done in accelerators more efficiently and not in CPU or GPUs is DataFlow. I talked to you about how the filters and inputs can be casted onto rows, onto these ALUs. So that whole process is called a data flow. And one example of data flow is out here. This is called a row stationary RS data flow. There are many data flows which are there, and this is one of the early ones. So what this row stationary data flow does is that you have your weights or filters, and you cast those filters onto these max, which are your ALUs here, multiply and accumulate. So each of these processing elements have the same weights as you go ahead in time. That means the weight stays in those memory elements and the input changes. A better representation is out here. So suppose this is the mesh of your processing elements or your ALUs. You see the same row one of the filter is casted onto first, second, and third element of the first row. And the second row has the second row of the weights, and third row has the third row of the weights. This way, what happens when you send the inputs to these processing elements do not need to fetch those weights again and again from the memory. And what they can do is after computing, they just need to send these weights vertically upwards, which is again faster. This minimizes the path data has to travel and thus minimizing energy. So this is one of the things that you can do using DL accelerators. There are many other things in these DL accelerators. For example, how do you exactly design that? Use analog circuits? Do you use mixed circuits? Do you use binary circuits? There's a whole lot of field, but that needs too much expertise to understand. So what I'll do is I'll finish this topic for now, but I'll go on to a more interesting topic, which is actually the second part of this pipeline. So we're working here in the hardware part of this pipeline, but what can we do on the neural network side of things? In fact, this field is called co-design of DNNs and hardware. What you do, you not only just design DNNs to work better on hardware, you design themselves together in conjunction with each other. So this whole pipeline is in a way optimized. That's why you see the big box here. And I'll tell you later on why data is also used. And this in some way is my favorite area in hardware for machine learning. I'll explain you the reasons later on. But let's see what are the techniques, what are different techniques available here when we co-design both DNNs and hardware. One of the things is pruning. So AlexNet, I'll give the example of AlexNet again 61 million weights. What we do is if we reduce the weights in this net, the size of the network would decrease. And if we reduce the weights, the things which we need to compute would also decrease. So it'll save both memory and energy if in some way we can decrease the weights. And this is what pruning does. So this is a fully connected network. But what pruning does, it just clears out some of these connections. So those weights are removed. And in some of the layers, it can also remove some neurons. So all the weights connected to that neurons are removed. So pruning this way, the network becomes lighter. One of the very naive, I would say, naive but effective pruning technique is this. So if you have your weights and you plot a histogram of your weights, you will see most of the weights are close to zero. Weights being close to zero, that means that these weights do not actually contribute a lot to your neural network's output. So what you can do is you can clear those weights out, just prune those connections which have close to zero weights and train the model again, and then you will get a histogram distribution like this. Of course, this is a naive pruning approach, but what many researchers have come across, have actually designed is you can make this pruning more hardware oriented. And that's the whole topic called hardware aware pruning. You can prune these networks in a way that it runs better on hardware. So let's take this example first. So this is the matrix which we need to multiply. This is a weight matrix of the neural network. And we have pruned it before. So you will see many weights of 0 up here. Now, when we cast these matrices onto our hardware, that is this array out here, what you'll see that weight 0, 0, weight 0, 1, weight 0, weight 3 are in processing element 0, and then is processing element 1 as these weights, as these weights. So if you count the number of weights in processing element 0, that's 1, 2, 3, 4, 5 weights up here. So you'll see that it'll take it 5 cycles to multiply these weights with the input and give the output. Similarly, you can count others, processing element 1, 2, and 3, as shown in the diagram here. You'll see that processing element 0 takes 5 cycles because it has 5 weights. Processing element 1 takes 2 cycles if it has 2 weights, and so on. So when you prune, you have actually sped up your model. So a dense model would have taken 8 cycles to process to do what this one whole multiplication, but your pruned model will just take 5 cycles. But you can do better than this. Instead of pruning the whole model based on the histogram of weights, you can just prune the processing element. So if I say each and every processing element will have 3 weights only and will prune out the rest 5 weights, what I get is a homogeneous sort of distribution of weights across processing elements. So across all your hardware, you have just 3 weights to be multiplied, and thus the whole multiplication takes 3 cycles. So these are the kind of techniques, where pruning can be attuned to your hardware. There are several others. For example, there is top K pruning. So you can use clustering techniques in your weight, in your processing elements here to speed this, to speed your model even further. And there is something called kernel-based pruning, where actually you prune the whole processing element itself. You'll see out of these processing elements, out of these 4 processing elements, which one of them has the least average magnitude of weights, and you can chuck it out because it's not going to affect your results that much. So pruning, not just pruning hardware-aware pruning, is one of the ways you can attune your neural networks to the hardware. For that, you need knowledge of both the hardware and the neural networks. Hence, the word co-design came into being. Another technique is quantization. What quantization means that you have a smooth distribution of weights, activation, and biases in your neural network. But in quantization, what you can do is you can group those weights into categories. For instance, let's look at this linear quantization scheme. You have this whole histogram of weights, and you have clubbed them into just 3, 4, 5, 6, 7, 8 values. So what you have reduced, you have reduced the number of weights to store. So what happens here is, suppose you have let's say 61 million weights. You need extra precision, you need extra number of bits to store these many weights. But when you quantize them, you need very few bits to store that weight. Reducing the number of bits not only reduces the memory your model takes on the hardware, but also reduces the amount of computation, because in some cases can reduce the amount of computation, not always. A major example of this quantization is Google Tensor Processing Unit, Google TPUs, or NVIDIA's Pascal GPU, both announced in 2016. Both of them used 8-bit integer rather than your 16 or 32-bit integer instructions, which you find on your laptops and the CPUs. And they've greatly reduced. We'll see the results later on of how efficient quantization has been. Again, as for pruning, quantization also has a lot of methods. You can also have clusters of quantization. You can use k-means cluster to cluster weights. You can also use clipping, as shown here. You can clip 2 high weights and quantize the remaining one of them. So again, there is a whole lot of literature covering the subject of quantization. What we'll go a little more detail in is an extreme form of quantization. That's called binary quantization. So what you do is you quantize your neural network, your whole neural network, your weights, biases, your activations, just to 2 values, that is +1 or -1. So this is your real valued network, which has 10 to 64 bits. But now your all binary network just has like one weight, has just one bit to it. And this extreme form of quantization has some consequences. We'll discuss it later, but one of the important things to note here is, remember you had this MAC operation earlier, you multiply the weights with the inputs and sum them up. When you binarize these weights and these input, what happens, this whole MAC operation multiplying and summing converts into a simple operation called XNOR gate. You might have heard about AND and OR gate. And this simple XNOR gate is very easily implementable in hardware and requires very less memory. So you can change all your, that you can just remove your ALU altogether and just put XNOR gates that will save not only energy, but also like your chip size would be reduced. And definitely binarizing the weights would reduce the amount of memory required to save the model. So people have gone actually a step farther than that. So not just using XNOR gates, they're using some of the techniques along with them. These are basically hardware techniques to make them even more energy efficient. One of the things is in-memory processing. And this is true not only for binary neural networks, but for other kind of processing also. So the general idea is, what if your memory can also do computations? I mean, it's a very it's a very interesting idea. Imagine your pen drive also doing calculations. It's something like that. So what researchers have found out that there are certain elements which can also store memory and perform simple computations. And one of the examples is this memory arrays, memory resistive arrays called memory resistive cross-point arrays. What it does is it not only stores your weights, but also you can multiply your weights within the memory itself. So the whole problem of fetching the weights from the memory is gone here. Another technique is mixed signal processing. So analog circuits are usually less accurate, less precise, I would say, than your digital circuits. But when you quantize, you don't need high precision as such. And that's when you can use analog circuits, which even save more energy and can be faster in some cases too. So using this XNOR, what a paper showed is like they combine these XNORs. You can see all these XNORs here to do the MAC operations. And instead of adding this, the outputs of XNOR using a digital adder, which a normal circuit would use, they accumulated that charge on a capacitor. If you remember some high school physics, if you send more and more charge to capacitor, the voltage on its plate would increase. And that's the idea they use for storing the outputs of a neuron in their circuit. So these are the two techniques which co-design of hardware and software kind of main techniques that they entail. There are several others which I'll discuss later. But I told you before that this is one of my favorite areas of research. But why is that so? If you know about deep learning, designing deep neural nets, it's still somewhat of an art. It's not a science. For example, it's some sort of black magic of how you come up with a very accurate deep learning model. You've seen models with hundreds of layers and thousands and millions of weights, but there's no set strategy on how to design those models. And that is also one of the major limitations of the field of deep learning, that how do these neural networks exactly work? Can we come up with a way to automatically design these neural networks? And there are considerable efforts in this direction also. You might have heard of AutoML, which does that. But unexpectedly, when you design neural networks for a hardware, some of the things come up which add to our knowledge of neural networks themselves. For example, let's look at our favorite, for this presentation at least, AlexNet. AlexNet original has 61 megabytes of parameters. There's 61 megabytes of parameters. And if after pruning, we can reduce it by 9 times and just take 6.7 megabytes on the memory now. So you've reduced your the size of a model by 9 times. But one might ask, that does pruning affect accuracy? And it does definitely affect accuracy. And you can see the number here. If you see top 1% error of AlexNet up here, it's 42.78% for the unpruned network, and for the pruned network is 42.77%. So actually it actually got a little more better by pruning rather than worse. Even the top 5 error got a little bit less. And you can see it with other networks also. For instance, let's talk about ResNet 50. You can reduce it to like 3.5 times, from 25.5 megabytes to 7.47 megabytes. But at the same time, you can also decrease the error by like 0.2% here and like a little more around 0.2% here again. Not just with pruning, let's talk about quantization again. So 32 bits is our general, our CPU uses, our GPU uses 32-bit precision. So these are convolutional bits and these are fully connected bits. So if you use 32 bits for convolution, 32 bits for fully connected, we get this 42.78 and 19.73% error in AlexNet. But when we quantize these weights to 4 bits and 2 bits, you will see we get 44.77% error and 22.33% error. So there is an increase in error by 2% here, so 1.99 and 2.6 here. But this is telling you something, that if you have reduced the number of bits to 4, that is like this is 4, 5, 6, 7, 1/8 of the number of bits that was used, we can still do away with accuracy, just 2% reduce in accuracy. And this tells you about how robust these deep learning models are, that even if you like prune 1/9 of the weights, or I mean, even if you reduce it to 1/9 of its size, and even if you quantize it, it bits to like 1/8 of the size, you can still get almost pretty much same accuracy as you did before, and in some cases even slightly better. So this is one of the major learnings from this field, that how these things like weights and connections and quantization affect neural networks. And most of the researchers have shown that it does not much. And I'll show you later how can these kind of things influence when we design our neural networks. And it is no surprise that some of the researchers who publish papers in tuning hardware for machine learning also publish in AutoML, because so much of new learnings come from this kind of research. For finally, our final side of the pipeline is up here, when we made a model of a biological neuron, a mathematical simple model. I'm mentioning this just for the sake of completeness of this presentation, that there is research being done that how can you make this model better. Now, this is a very simple model of a neuron. You have weights, you have inputs, you multiply them and add them. How can you change this model itself? So there is considerable effort being done in neuromorphic computing. One of the key ideas here is that your weights and outputs of these neural networks are not just one numbers, but they are actually kind of waves whose magnitude and the duration of that wave also matters. And it has been seen that the energy efficiency of these chips, of these neuromorphic chips, might be better than those ones which we are using now. But this is still not very popular because the hardware resources are available only with a few companies. For example, IBM's True North is one of the key players. You must have heard of this name in this domain of neuromorphic computing. But I'll only briefly mention it for the sake of completeness. So just to finalize things up, I'll just mention 2 other techniques, and again, which will kind of echo the idea of how tuning networks for hardware is also helping us gain more knowledge about these networks. For example, so you can also exploit data statistics in your data. For example, you can use ReLU activation functions. A ReLU activation function is neural networks, pretty popular. And what happens is that when you send negative values through ReLU, they get 0. So you will see a lot of zeros in the output of ReLU. What that means that for the next layer, you don't have to do these operations because the result is 0. When you multiply them with anything, the result would be 0. And that's what one of the papers did. What they did is they added a gate just to check whether the output is 0 or not. And if it's 0, they don't compute for that output. And what they found, that they could save 45% of energy using this. So now suppose I'm a neural network designer and I'm designing some network. I choose ReLU, I get 94% accuracy. I use some other activation function, let's say 10H. What I get 95% accuracy. So there is 1% improve in my accuracy. But when I look at the hardware, I'll see that the ReLU actually saves 45% of the accuracy. So that trade-off now is not just about accuracy also, but also it's about energy. I might end up using ReLU in some of the cases. And another thing where this has deeply influenced neural network design is knowledge distillation. So in theory, even like a 2-layer neural network can learn any function given there is enough data, but that is not practically possible because very shallow networks are difficult to train. That's why you have very deep networks. But what knowledge distillation does is like you train a big network, you call it the teacher network, and you train a smaller network, you call a student network, to train on the outputs of this teacher network. What happens that it learns whatever this teacher network does, but in much less layers and much small size of the model than the teacher network. And you will see these techniques being employed in hardware, but even more in increasing the accuracy of neural networks itself. So you can come easily across papers where they'll have their normal neural network will be doing something, but they will add another branch to it, another student branch to it, just to increase its accuracy in some way. So there is this thing coming up again, that how hard tuning the networks for hardware are actually influence the networks themselves. So I think I'll leave you up here with all these things. We discussed various techniques. These are some of the references I used. It's a big field, but it'll give you a flavor of what these field entails. And now, if you have any questions, I'm up for it.